Okay, so I think we have in the last class we have discussed already about basic theory of probability, right. So, that is something we started discussing. We have already proven Bayes theorem, we have given the definition of random variable, that is just like a mapping from events to value in real axis. So, that is something we have started, and then we defined something where the random events are discrete, that means it is countable. So, whatever events that will be happening, that is countable, like you toss a coin. So, you have only two outcomes that you can map to a real axis, maybe put to 0 or 1 or means head and tail or -1 or 1, but it is just countable. So, for that we started defining corresponding probabilities of each events. Okay. So, we have given a definition that is called where x is the random variable, it is actually saying the probability that random variable x is equal to a particular event x I or the real axis representation of that event x I. What is the probability, associated probability of that? And we have also told, because if we just consider all the events and their probability, if we just sum them, that is a certain event, because we must be seeing something is happening. Okay. So, like we say probability of head, that is let us say x equals to -1, that is probably tail, probability of tail is half, and then we say probability of head, that is +1, that is equal to half. So, if we just add these two, that means something will be happening. So, that is a certain event, and that addition of probability must be 1. So, we have also given a fundamental theorem of probability theory, that is called this summation when it is taken over all the events that can be occurring in that particular experimentation, that must be always 1. So, probability actually sums up to 1, the way we have defined probability of a random variable, okay, or associated probability for a particular random variable for a particular value when it takes a particular value. So, this is always true, that is something we have already discussed. Okay. We have also discussed something called means same representation for joint event, where you have two random variable for two events. Okay. We have given one example of such thing. So, if we have joint event, so we can represent it as this x and y. Okay. These two are joint event, that means x represent the random variable associated with the experimentation where we are considering that event x or collection of event x, and then collection of event y if we have that. So, to separate this one, and then we say probability of x y x I y I, that actually means that probability that random variable x takes value x I from its sample space, and simultaneously random variable y takes value y I from its sample space. Okay. So, this is something which can be defined. This might not be just same I, this might be also y j, because that might have a different variability altogether. Okay. So, this is called that joint event and associated joint probability. Okay. And similarly, if we just sum this over all the possible combination of x and y's, we must get 1. So, if we just sum it, it will be a joint summation, because I have to do combination for all x and y. So, this is for all I going from 1 to n and all j going from whatever value it goes. So, let us say this is n x and this is n y. If we just take all of this, that must be 1. Okay. So, this is for joint event, and accordingly we can keep on augmenting that. We can have as many events jointly happening as we wish, and accordingly the joint distribution will be formed. Okay. So, after defining this with this same definition or notational aspect, we started defining the conditional event, right. So, we have also told that the conditional event, which is represented as this, Okay. So, this x given y, it is actually a conditional thing. That means, there are two random experimentation simultaneously going on, which have some random outcomes. One is represented by a random variable x, which is already mapped to a real axis, and the other one is represented by random experimentation, which is or random variable y, which is mapped to again real axis. Okay. So, x given y means that I have already observed the event y, which is taking value equal to yj. Given that, what is the probability that I will be observing that x is happening to be xi, that associated probability. This is that conditional probability we talk about. Okay. So, whenever we say this is conditional probability, so if we just sum this over I, okay. So, what do we expect? This is a conditional probability, that means y, yj, that is already given. Okay. Given that all the possible probability values for seeing the event x equals to xi. Okay. So, if I take all of them, that must be again giving me probability of 1, because given that yj has happened, if I am just trying to test what is the associated probability of each of the possible outcomes of xi and their associated probability, if I add all those, that must be a certain things, because something of those xi will be happening anyway. So, that probability becomes 1. Very simple example that we have taken, probably we had two joint observation. You remember that we were just trying to roll a die, and then we were saying whether it is even or odd, that is one event, and then there was another event that it is less than 4 or greater than 4. Right. So, if suppose I say it is already even, that is known, that is yj for me, that it can take two outcomes, even or odd. So, I am just saying that given that it is even, okay. That means only 2, 4 and 6 are possible outcomes. Okay. So, only those cases I will be taking. So, I will be rolling the die, it is a random experimentation of course, but I will be only marking those events where either 2, 4 or 6 is happening. All other events are non-entity for me, because they are not part of this experimentation. Okay. So, I will just take those things and start counting that frequency definition of probability theory, and then what I will say, I will try to see a particular xi is happening, whether it is less than 4 or greater than 4. Okay. These two things are there. So, here if you see less than equal to 4 are 2. So, there are 2 favorable outcomes towards this and 1 favorable outcomes which is not towards this. So, this xi I can say, or this x I can say it is less than this or greater than this. Okay. So, if this is my definition of two events and accordingly xi is defined. So, xi will take two values only, let us say 0 and 1, again I am mapping. So, 0 means actually it is less than 4, okay, less than or equal to 4, 1 means it is actually greater than 4, and then if I just evaluate the calculation or probability calculation, what is this value? Suppose let us say 0 given it is even, okay, or let us say even I represent as 1. Okay. So, even and odd, these are two events which are mapped to the real axis. I say this is 1, this is 0. Okay. As I have told, both the events x and y, or both the experimentation x and y and associated random variable must be going to the real axis. So, this has gone to the real axis, I have just denoted 1 and 0. Similarly, less than equal to 4 and greater than 4, these are the two outcomes, this must be mapped to a real axis. So, let us say I put it as 0 and let us say I put it as 1. Okay. So, whenever I write this, that actually means that 1 has occurred in y. So, that means this has occurred. So, it is already even number. Given that it is even number, what is the probability that this has occurred? Okay. That means it is less than 4. This probability I wish to calculate, I have already seen that there are 1, 3, 5 also. Out of them, these are only my favorable condition towards this y event, that y equal to 1. Out of them, what is the probability that this x will be 0? So, there are 2 favorable outcome towards that and 1 non-favorable. They are equally likely because the phases are equally likely to come. So, I can very fairly say that that should be 2 by 3, that probability. because 2 favorable and overall means possibility are 3. Similarly, P x y, if I wish to calculate 1 1, that must be 1 by 3, because 1 means this greater than 4, there is only one favorable case out of 3. So, that must be 1 by 3. If you sum them, that should give you 1. Okay. So, with that simple experiment, we can actually again map it towards a conditional probability calculation, and we can get back to this theory. That is very important, that conditional event, if the condition upon which it depends on, that is already fixed, then if you just take a summation over the one which is dependent on, if you just take a summation of all the probabilities on that random variable, you must be getting 1. Similarly, it should be also true if I put it like this, P y given x, suppose it is the same experiment, I just now turned the condition. Okay. So, given that it is less than equal to 4, what is the probability that this is even or odd, something like that. Okay. So, then y j must come over here and x I. So, now it is given x I, I am summing over all j, this must be also giving me 1, that should be always happening. You can again test it with that same experiment we have done. Okay. So, you will see that this is happening for all possible cases. Okay. So, these two are very important relationship, and then we have also understood the Bayes theorem. Okay. So, what is Bayes theorem? Bayes theorem we have called, this is the joint event we have already talked about, x I and let us say y j. According to Bayes theorem, that must be the conditional one multiplied by which is the independent thing, means on which the whole experiment depends. So, P x given y, suppose x is conditioned means over y. So, that should be x I given y j P y y j. Be careful about the notation, whenever it is conditional it should be like this, that random variable x given random variable y. Whenever it is not conditional and it is a single random variable, so it should be like this. Whenever it is joined, it should be like this. Okay. So, that is the notational means representation. Okay. So, this must be happening, and it should be also true for y given x. Okay. So, Bayes theorem tells me that this is true, right. So, now let us try to evaluate something like this, P x y, that is the joint one I am taking, and I sum it over one of them. Okay. Let us say I sum it over I. Okay. So, I can write over I will be summing P, let us give take this definition, this x given y. Okay. So, x given y. So, I am just writing the expanding the joint distribution, okay, or joint probability with the conditional one. So, x I given y j P y y j, I can write it this way. Okay. Now, this particular part that does not depend on I, so I can take that out. So, I can really take this P y y j out, summation I P x given y x I given y j. Right. Now, this already we have proven that this should be 1, we have just now proven that. Okay. So, if this is 1, this must be P y y j, that is a fantastic thing. What is happening, if you take the joint distribution and we call this as marginalization, if you just sum it over one of the random variable, okay, all possible cases of that, we will be getting the marginalized distribution, we call that. So, this is actually from the joint distribution we can get the individual distribution. Similarly, we can do it for x also. So, we just have to sum it over j, I will be getting P x x I. You can try this, okay. Just have to use the other one probably. Okay. So, this is how you can always, any joint distribution given, you can get the individual distribution, okay, that is possible if we call this distribution. Okay. Basically this is called actually a probability mass distribution, probably we have not mentioned that. So, because this is discrete event, so whenever we get for a particular random variable Px xi, we know all the values of this for every possible values of xi, we call this as a PMF or probability mass function. Okay. So, and if you just plot it, it should be like this. All those xi, they are, now we have mapped it to a real axis. So, there will be some value, some discrete value over this particular thing, and there will be a associated probability value which will be plotted over here. And we know that the sum of all this probability must be 1, that has to be, and they must be always positive, because it is probability value, probability cannot be negative, because you will be, see, the frequency definition of probability says that I will be doing this experiment for let us say infinite number of time, out of them how many will be in favor of my x equal to xi. Okay. That can never be negative, neither that n can be negative, nor that how many means with what frequency I will be getting a favorable outcome, that can at least be 0, it cannot be less than that. I cannot have a negative event happening, a negative count of event happening. So, I will be always getting a positive number. So, definitely the probability value, associated probability value, whether it is small or big, it should be some positive thing, and sum of positive should be giving me 1. So, therefore, I can very fairly say from this that P of x xi must be lying between 0 and 1, because if their sum is 1, individually they must be fraction. Okay. So, this is always true for any probability mass function or any probability value. Okay. So, these are something which are already known to you. Okay. So, what we have now learned is, we know how to define in a for a discrete random variable, how to define joint distribution, and from there how to marginalize to get individual distribution of each of the random variable, that is something we know, and the associated conditional distribution, how it is related to joint distribution. This is something we have already derived. You might be now asking all this Bayes theorem, conditional rule, what that has to do with communication. So, let me just give you a simple example which might not be having anything to do with analog communication in particular, it is mostly the application is in digital communication, but you will see later on when we will be proving something on analog communication, there are some requirement of that also, but I will just give this example because visually this is very satisfying. Okay. So, let us try to take this example that this is my transmitter and this is my receiver. So, from the transmitter side, why I am giving this digital example, because you will see that there are only very possible number of symbols that can be happening. So, definitely you will have to calculate probability values for a less number of events. Okay. So, that is why it is little bit easier to tackle. So, let us say from the transmitter side, I can only transmit two possible kind of signal. Okay. One is high voltage, or let us call it 1, and one is a low voltage or almost 0 voltage, which let us call that 0. Okay. So, it is almost like a binary bit stream which you are trying to transmit, and that probably carries information as long as it is properly encoded. Okay. So, it is streams of 1s and 0s I am trying to transmit with some symbol. Okay. So, let us say at the transmitter there is a, because we are transmitting events, so there is a random occurrence of these events with, let us call that a variable x. Okay. X can take 1 or x can take 0. So, these are the possible two possible outcome, and associated there are some probability. Okay. So, let us say with q probability at the transmitter side it is 1, and with 1 minus q probability it is 0, because only 2 are there and their probability, sum of the probability must be 1, we have already seen that. So, this is the only possible scenario, okay, because we only have 2 events or 2 sample values. Okay. So, this probability that xi equals to 1, okay. So, this is q and probability that x, this xi equals to 0, 1 minus q. Okay. These are called the prior probability. What does that means? That while transmitting, this is the probability with which I generate either 0 or 1. Okay. So, that is why these are called, means without seeing what is happening at the receiver, this is what is actually happening at the transmitter. So, this is called the prior probability, that means before transmission this is the statistical balance between the events, okay, which we are trying to transmit and decode on the other side. Now, we have already talked about channel. So, we will be this 1 or 0 whatever it is a voltage level or some specific type of symbol, whichever way we represent it, we will be putting it in the channel. Okay. Now, channel will do its own corruption, it will probably add noise, it will distort things and all those things will be happening, and at the end at the receiver will employ something to detect it. Okay. But what will happen, because the channel has already corrupted it, I might have a wrong detection at the receiver side. Okay. So, there might be erroneous detection at the receiver side. So, what might happen, suppose I transmit and let us say this, I still say this is y, okay, random event y, which is the reception. Okay. Now, because this is already random, in between whatever things are happening, that is also random. So, what I will be receiving, that must be a random things. Okay. So, that might be 1 and that might be also 0. So, I have only two possibility, I already know that whatever he is transmitting, that is limited to 1 or 0. So, whatever I will be receiving, somehow I will be encoding this and I will be detecting only 1 and 0. Okay. So, this is two things I will be detecting. Now, what might happen, because of the channel there might be error. So, that I transmit 1 and he also receives 1, this has certain probability. So, let us call this 1 minus Pe, where Pe is the error probability. So, immediately I can see that I transmit 1 and 0 is received, that must have a probability of Pe, because again these two are the only possible, that once I transmit 1, there are only two possibilities, that either I will be receiving 1 or I will be receiving 0. So, there are two possibilities and we have already told that sum of probabilities must be 1. So, if error probability, that 1 gets flipped to 0, if this is Pe, somehow I will have to calculate that, you will see in your digital communication how to calculate that. So, if this is Pe, that must be 1 minus Pe. Let us say that same thing happens for the 0 also. So, the probability that I will be correctly receiving it, that 0 I transmit and I receive 0, that is 1 minus Pe, and I will be means wrongly receiving it is Pe. Okay. So, that is what happens in the whole scenario. Now, of course, you will be asking how do I evaluate Pe, that is a separate domain. Okay. We will have to see how do we evaluate those things, but that will not be part of our discussion in analog communication, that should be the part of digital communication discussion. Okay. But whatever that is, this is the scenario. Okay. So, now let us try to define whatever we have got so far. So, if you see over here, there are two random events. Okay. One is this x, which is one of the random variable, and the another one is the y, what is transmitted and what is received. Okay. Both of them I have now mapped into real axis, it can take value 0 and 1, other one also can take 0 and 1. Okay. So, I know the prior probability, which is Px 1 I already know. Okay. Px, that random variable will be taking a value 1, that I already know, that I have told q, and Px 0, that is 1 minus q, right. Now, over here whatever I know, those are the conditional probability, if you see very carefully. So, I am just mapping whatever we have learned to a physical example. Okay. So, this is the conditional probability, that given 1 has been transmitted, what is the probability that I will be getting 1 or 0. Okay. So, I can immediately write that P y given x 0 0. Okay. That means that x, that is the given one, that was 0, 0 was transmitted. What is the probability that I will be getting 0? That must be according to our definition 1 minus Pe. Same thing will be happening according to our definition, it is symmetric actually, 1 and 0 are both behaving in a symmetric manner due to the channel. So, P that y given x, and I will be transmitting 1 and I will be receiving also 1, these are all 1 minus P. Okay. And just the other thing, that P y given x, I will be transmitting 0 and I will be getting 1, or P y given x, I will be transmitting 1 and I will be getting 0, this is P. So, what I can see that I already know all the possible conditional probabilities, right. So, these two things I know the prior probability. Now, I will apply Bayes theorem. So, I know y given x, I want to now know what is the probability that x given y. Okay. So, this is something I wish to know, and also I wish to know what is the probability that I will be receiving 1 or I will be receiving 0, that is actually the receiver probability. Okay. So, that is the marginalized probability coming from the joint distribution. So, if I can define now P x y and this x I y I or y j, if I can define this, I have already talked about marginalizing. So, I can marginalize it over x and then I can get P y. Okay. So, there is a possibility that I can now get, like prior probability, this probability of, earlier I was defining probability of transmitting something. Now, due to the channel there will be something else which will be happening. Now, I wish to know what is the probability that I will be receiving 1 and what is the probability that I will be receiving 0. So, that is something, now I have enough tool to calculate that. Okay. And you will be asking why I need the reverse thing, that means P, now I will be evaluating x given y, right, with some values. Why do I need this? So, in detection, what mostly you are interested, that at the receiver I detect something. Okay, after doing all those things I just see, okay, this is 1 or 0, finally I will be taking that. Now, whether it is, if I detect that as 1 or 0, I need to understand that, okay, I have received 1, but I have a doubt because the channel was creating errors, I have a doubt whether 1 was transmitted or not. Now, I wish to know if I have received 1, was it 1 and with what probability? Was it 1 actually transmitted and with what probability? That should be given by this P x given y. So, now given thing is known to the receiver, because receiver will be receiving that. Receiver does not know what was transmitted, he is trying to guess what could have been transmitted. So, from this he will be able to backtrack or back calculate this particular information. Okay. And then he will be able to guess probably what kind of error he is expecting, right. So, after detecting what is the overall error that he is making, because once he has this probability value, he will be knowing that how many of those things, means if he knows the probability of error, he will be also knowing if I receive this many, out of the definition of frequency, definition of probability, we can always get to know how many of them will be in error. Okay. So, this is something he will be knowing, and then he can actually try to manipulate that. But if he does not know this relationship, he will not be able to manipulate that. Manipulation means probably he has to design a better detector, he has to probably use a different channel where the error is less or error is more, or some other things he has to put over there. Okay. So, all those things he can do only if he has, or the receiver has, this understanding. Okay. So, that is why it is very important that we have this mapping, all the conditional probability, marginal probability and the overall distribution, that is well known, and if one is known, how to calculate the other one, that is pretty much required in any communication. So, what we will do now, we have so far done even the example done for discrete case. We will just now try to see what happens for a continuous case, which will be more interesting for us in analog communication especially. Okay. Thank you.